Hello, everybody. My name is Jose Antonio Nunez. I am an electronics engineer with experience in the aerospace industry. Currently, I am studying for a Master of Science degree in Applied Physics at the Engineering Institute of the Autonomous University of Baja California, located in the north of Mexico. And today, I want to present you an advance of my thesis research project entitled Reduction of the Relative Positioning Error of a machine vision system using friction compensation, having as co-authors my professors Lars Linder and Oleg Seryenko. In my master's degree work, I am working with a novel 3D laser scanning system under development in the Engineering Institute. It represents a laser scanning system that uses DC motors for the positioning laser and the scanning aperture. Our 3D scanner can be moved in 3 dimensions by using a turn motor on this side. This TBS implements the dynamic triangulation measurement method to determine the 3D coordinates of any object under observation. This presentation will show the relative positioning error estimation of the control DC motor for the positioning laser of the TBS number 3. Using friction estimation based on the Luger friction model. Then is presented a feasible solution for positioning control using friction compensation. And finally is presented the computational simulation results that I received. You can use the laser scanning system to determine the 3D coordinates for any object surface on field of view. So an advantage of using DC motor for the laser scanner is that the system has a continuous scanning field of view. Previous research has shown the advantage of using high quality DC motor for the TBS to eliminate nonlinear effects like the Coning torque and reduce the inherent breakaway torque wherever a relative angular positioning error is still presented and can be attributed to the friction torque. The friction is a complicated phenomenon that arises in the contact between two surfaces. There are many different proposals for friction modeling. Reasons are, for example, getting insight into the physical aspect or minimizing undesired effects in control systems. It is common to assume for the classical models the friction force as a friction of the relative velocity, sliding velocity. Only for an exception, the friction at rest or static friction before the breakaway force occurs and initiates the sliding regime can be described as a function of the applied torque. The Strivik observed that the friction force does not totally decrease from the breakaway force to the column level, but the velocity dependence is continuous. Friction is a phenomenon that can be fully described using only the static model presented above. Differential equation also can describe it. The dynamic friction models usually consist of a force equation and a state equation. On this slide, two important dynamic friction models are presented. The first is the Tal model. The Tal model is based on the consideration that the origin of the friction is in quasi-static bonds that are continuously formed and subsequently broken. The Tal model does not include the distributed effect nor stiction. In the case of the Luger friction, Canada de Witt proposed the Luger friction model, which represents a generalization of the Tal model, which considers the Strivik effect. So the Luger friction is a realistic model that covers almost all experimentally observed phenomena and is relatively easy to identify and implement in control systems. Here you can see in figure 3 a diagram of the laser positioning system of the TBS number 3. In this system, the laser beam position in the scanner field of view correspond directly to the DC motor shaft angular position. So the model of the DC motor is derived in this slide. The starting point is the model of the DC motor with permanent magnets neglecting nonlinear effects such as the breakaway and cooling torque. The figure 4 and the transfer function equation present this model. So the mechanical section for the DC motor can be expressed in this equation. And in order to integrate a nonlinear friction model, the motor damping given by air, by the parameter air, is replaced by a nonlinear friction force. Rewriting the mechanical section with the lower friction model, we obtain this equation, where alpha 2 represents the viscous damping friction coefficient, and F the nonlinear friction component of the lower friction model. The table 1 is summarizes the parameters of the DC motor model using the real data from the DC, for the Maxon Max 29, and in order to implement the lower friction, the model parameters have to be defined. The parameters were derived and estimated using the model properties and supported by a parameter estimation tool of MATLAB. This tool estimated the model parameters and initial condition importing and processing experimental data using a least square approach. And the parameters for the lower friction model are summarized in this table. The figure 5 shows the complete simulation model of the DC motor with the lower friction model. And this equation is used to calculate the time that the motor rotates an angular reference position when doubling an armature voltage. To implement this positioning algorithm for simulation is arbitrarily established the angular reference positioning 25, 35, and 45 degrees. And the figure 6 shows the simulated actual angular position over time for open loop positioning control of the DC motor with the lower friction for the different reference angular positions. This equation defines the relative angular error in the steady state, and the table 3 summarizes the applet pulse time duration, the resulting final angular position, and the relative angular error. According to the simulation results, for a reference of 45 degrees, exists a relative positioning error of 2.82%, 3.35% for 35 degrees, 4.04% for 35 degrees. So in order to perform a nonlinear proportional derivative control, the proposal is to implement the following nonlinear function, which represents a simple model-free sorb control. So to reduce the relative positioning error to friction torque, the sorb control is applied as figure 7. To implement the sorb control, the gains parameters Kp, Kt, and Kr must be defined. The summarized gains in the table ensures the global asymptotically stability with Lyapunov direct method for the closed loop positioning system. So the figure 8 shows the angular position over time simulated for closed loop position control of, for the DC motor for the same reference angular position from figure 6. It is shown that can be performed a significant reduction of the relative positioning error implementing the SORP control proposal. It is shown a fast and precise positioning for the DC motor, demonstrating that the proposed SORP control provides a feasible solution for high performance positioning for the laser scanning system. So as conclusions, friction theoretically affects the positioning accuracy of the laser scanner. This is demonstrated, and the relative angular positioning error of the DC motor shaft was identified and modeled using the lower friction model. So the respective parameters were derived using the model properties and processing experimental data. So the computational simulation of the proposed open loop and closed loop control algorithms was developed and carried out using DC motor maximum Remax 29 of the TPS number 3. And then it's demonstrating that the proposed SORP nonlinear control provides a feasible solution for high performance positioning, performing friction compensation on the laser positioning system of the TPS number 3. So in further research, we'll review more existing dynamic friction models to estimate the relative angular position error of the laser positioning system. I will validate the control effectiveness using different nonlinear friction models for the DC motor of the 3D laser scanner systems to perform the friction compensation. And the reduction of the laser scan of the laser beam final position error will be carried out using friction compensation experimentally with the different high quality DC motors with appropriate characteristics for the TPS design. It is expected to ensure a robust control design using friction compensation. Finally, thank you very much to everybody for your attention. I will remain attentive to your questions or comments, also in my personal email. If anybody wants to contact me later, I am open for discussions or often open for maybe a future collaboration. These are the reference for the presentation. So thank you everybody, and expect you to have a nice day.